Okay, great. So welcome to 106B Project 4 on safe control for multi-agent systems. Okay, so in this project, we're going to go ahead and do a couple of different things. First up, we're going to program a feedback linearization controller for a turtlebot system. So these are those special controllers that make systems that are nonlinear act as if they're linear, just using feedback control. Okay. After this, we're going to go ahead and implement a special type of controller called a CBF-QP that will allow us to deal with multiple turtlebots at once in a very safe and reliable manner. After this, we're going to go ahead and change some of our assumptions on that QP and say, now, each turtlebot is just going to interact with its environment using computer vision. Okay? So we're going to have a vision-based safe controller for multiple agents. And after this, we're going to finish up by implementing things on hardware and showing that these techniques actually do work outside of a simulation environment. All right, great. So what is feedback linearization? Let's go over a very, very brief review of some of the concepts and motivating ideas behind it, okay? So this core question behind feedback linearization is this idea of how we can transform some nonlinear system that might have some complicated dynamics into a purely linear system just using pure feedback control, all right? Because we know linear systems are very nice and easy to deal with when we're trying to design controllers. And nonlinear systems, if we just take them head on, they can be quite difficult, right? So our main question in this portion is how we can actually apply feedback linearization to a system like a turtlebot. And once we've made it linear, how can we actually design a tracking controller for that linear system? So these are going to be these two questions that you'll be answering in this first component of this project. All right. So you might remember from earlier in this class, we came up with this technique called dynamic extension from one of your homeworks to actually deal with this case where we want to apply this feedback linearization to a turtlebot. So what dynamic extension is it's essentially a process that allows us to invert these nonlinear dynamics of the system. Okay, so let's go ahead and walk through step by step what we're going to do. All right, so let's imagine that we have some desired trajectory to our system, right? Maybe we have like an X desired and a Y desired position for a turtlebot. What we're going to do is we're going to feed those into this linear system over here, right? This is like the innermost linear layer of our system, purely linear dynamics, all right? So on that linear system, we're going to figure out an input Z, okay? And once we have that tracking input Z that allows us to track our trajectory, we'll pass that into another input called W, all right? And this is one layer further out, right? We're getting closer and closer to our original nonlinear system. So we perform some inversion, we get this more nonlinear input W. And once we have that input W, we're going to integrate one of the terms with respect to time to get back to our original input U, to our fully nonlinear turtlebot dynamics, okay? And once we plug that input U into our original system, we'll get an input U that makes our system A, behave like a linear system, and B, track this desired trajectory, just as this linear system would, okay? So we're going from this process of, A, canceling out these nonlinear dynamics, and B, finding this tracking input Z that allows that linear dynamics to track our desired trajectory. Okay, so something that you might notice over here is that there's an integral contained in this, right? We're integrating this v dot to get back to our original input u for our nonlinear system. So how do we actually perform this in code? This is something that we'll usually have to use a numerical integral to solve for, all right? So how this is actually implemented in your project will be entirely up to you, but you can use something like an Euler integral or maybe a more advanced technique if that's something you're interested in trying. Okay. So how do we actually design that linear tracking controller, right? How do we figure out that input Z that allows this linear system to track this desired trajectory? Well, here's what we're going to do, all right? In this case, we're only actually going to care about the X and Y components of our turtlebot's trajectory. We're not actually too concerned with the heading angle of our turtlebot in this case. So phi in this case, which represents our heading angle, can really be anything, right? We don't worry about it too much. So what we have access to is we have our desired X position for our turtlebot, our desired Y position of our turtlebot, and then the first and second time derivatives of those desired positions, all right? So what we're trying to do is we're trying to figure out an input to this linear system, right? This is our innermost linear layer in our system, trying to figure out that input Z that allows us to track that trajectory in a really stable manner, okay? So what would that input Z be? Well, as a hint, you could try looking at this differential equation over on the right, which is a second order differential equation that describes the tracking error of the system, okay? So we know that by selecting certain values of C1 and C2, right, we can make this error converge to zero exponentially quickly, right, and do that in a really stable manner. So what you can try is using these linear system dynamics over here, right, and using the desired trajectory, Q desired of T, and its two time derivatives, try and figure out an input Z that transforms this relationship into this relationship over here, okay? So try and extract the second order differential equation outside of this, and soon you'll be able to get a tracking controller that will converge exponentially quickly to this desired trajectory, okay? So I just want to highlight, this isn't the only way of tackling this problem, all right? This problem is actually purposefully open-ended. You could really solve it in any way that you want. Say you want to use LQR tracking control or a control the op and off function, go for it, all right? As long as you're using feedback linearization in there, any technique that you use for that innermost tracking layer will be perfectly valid. Okay, so after you've implemented it correctly, you might get a response plot that looks a little bit like this, right? So our turtlebot's going to start over here, and our X position will try and reach this desired X position of 0, and our Y position will try and converge to some other desired Y position as well. So if you've implemented your controller correctly, you should see X and Y plots that look something like this. Your phi, your V, and your omega, these are things that may actually depend on your control technique and your gains that may use, but make sure your X and your Y look fairly similar to this. Okay, so with that, let's go ahead and talk about control barrier functions, all right? So let's imagine that we have a system of many, many turtlebots, right? Not just a single turtlebot. What we want to do is we want to try and come up with a method of encoding the safety of each turtlebot with respect to others using some sort of scalar function, h, right? So this function will take in maybe the state vector of our individual turtlebot right over here, and the states of these other turtlebots in the system, right? And it returns a single scalar value that tells us if our turtlebot is currently in a safe state or not. So if our turtlebot is safe, that function h will be greater than 0. If our function, or excuse me, if our turtlebot is like right about to collide with one of these other ones, that barrier function h will be equal to 0. And if our turtlebot is actively in collision with another turtlebot, that barrier function will be less than 0. Okay, so that's our criteria for this function h over here. So the way we're going to design it in this project is we're going to consider what are called like pairwise safety constraints, all right? So we're going to have the turtlebot that we wish to control, which we'll refer to as the ego turtlebot in this project, and we'll have an obstacle turtlebot over here, all right? So what we're going to do is we'll be like, hey, what's some function h of our state vector of our ego turtlebot that will, based on these three criteria over here, tell us if we're in a safe state with respect to this single obstacle turtlebot, okay? So this function h, it has many different forms. This will again be something that you will have to come up with yourself. Okay. So let's talk about the deadlock CBF-QP controller. What we're going to do now is we're going to use that pairwise safety barrier function that we came up with, right? That encodes our safety with respect to another turtlebot. We're going to use that barrier function to enable a system of multiple turtlebots to move around safely and still be able to track trajectories, okay? So you might know already from discussion or lecture that there's a type of controller called a CBF-QP that usually allows us to do this, right? And traditionally, how this controller works is we send in a tracking control input, right? And it returns a safe version of that tracking control input after we solve the CBF-QP, okay? But the problem is with our turtlebot system, if we were to apply that like directly to our tracking input U to our system, right? That one that we generated from feedback linearization, our turtlebots actually won't figure out how to steer around each other, right? They're going to get stuck in these sort of face-off scenarios, like you can see down here, called deadlocks, all right? So if we just apply it directly to that feedback linearizing input, we're going to end up with these deadlock situations. So we want to figure out how to resolve these so none of our turtlebots get stuck in face-offs when they're trying to go ahead and track their own trajectories, all right? So let's discuss how we can actually resolve this deadlock scenario and make our turtlebots steer around each other while still tracking their trajectories, all the while remaining safe, all right? So it's a kind of tough problem to solve. So what we're going to do is, instead of putting our CBF-QP over our outermost feedback linearization input, right, that final input U that we came up with, we're going to embed it all the way inside our feedback linearizing controller, okay? So you might remember that we tried to come up with that tracking input Z, right, that would allow our system to track our desired trajectory, But that input Z was to the linear system, right? That innermost linear layer. So what we're going to do is we're going to say, okay, we're going to solve this optimization problem with respect to that innermost linear system to figure out what our safe input to our system should be. All right. So let's talk about this problem in a little bit more detail. Okay. So there's a couple differences with respect to a standard CBF-QP problem. Normally, we wouldn't have this little matrix Q in the middle. But what we want to do is we want to really encourage our system to steer around other turtlebots. Okay. So what that means is that we're going to use this matrix Q to essentially weight different terms in our input vector Z differently, right? We could assign more weight, much more cost to, say, a braking term and much less cost to a steering term. And that way, we can encourage our system to use steering to figure out these safety constraints, all right? So we'll use this matrix Q. We could change the different elements of this matrix Q to weight terms in our input differently. And that way it'll be able to prioritize steering around these different obstacles, okay? So what we're gonna do after that is in our optimization constraint down here, this is called a barrier function constraint, right? It might look a little bit different to what we might have discussed before. This is actually called a high relative degree barrier function constraint, all right? And the reason we have to do this is that we're applying our barrier function over our innermost layer, right? We're applying it over our linear system, Q dot equals A times Q plus B times Z. So it turns out that our innermost linear system will require that we take two derivatives of our barrier function instead of just one. Okay. So once again, something that you could see over here is that our input Z only shows up in our second derivatives of X and Y, okay? So that's why we actually need to end up taking that second derivative of our barrier function constraint, because to actually get that input term Z to show up in our barrier function constraint, we'll need to have those second derivatives of X and Y in there. Okay. So our main challenge now is that we want to figure out how to decide this value of K1 and this value of K2 such that this constraint, which constrains whether we're in the safe state or not, and tells us what values of Z we can actually use, we want to figure out how to select K1 and K2 such that H is always greater than 0, okay? Because when H is greater than 0, right, we have that our system is in a safe state. So what is this K1 and K2 going to be? Turns out there's going to be a very specific set of criteria on K1 and K2, and this is something that you guys will have to work out yourselves, all right? So as a hint for getting started on this, try solving this differential equation for H as a function of time, all right? Once you solve this differential equation, maybe you'll see what values of K1 and K2 you'll be able to pick such that H of t is always greater than 0 for all time, okay? So let's summarize what we're doing in this controller, all right? First, what we're doing is we're using our tracking controller, that nominal tracking controller, to figure out the tracking Z input to the linear system, okay? So once we have that linear system Z tracking input, we apply our CBF-QP around that, right? Applying one barrier constraint for each of the turtlebot obstacles, okay? So once we've applied all those barrier constraints and we've solved that optimization problem, we'll have a safe input Z to our system. Now, applying the process of feedback linearization, we then convert that Z input to an input W using this equation over here, right? We'll have to invert this relationship. And after we've done that, we'll convert our W input back to our original U input to our system using that integration method we discussed a little bit earlier, okay? And finally, that'll give us an input U to our system that's safe and that allows us to steer around these obstacles, okay? So it's a little bit of a complex procedure, but it'll really enable us to do a lot of great things with our safety critical control. So just to show you guys what the solution might end up looking like, we see 5 turtlebots with conflicting objectives, all avoiding each other and getting to their goal locations, all right? Let me let that play one more time. So they'll come together in the middle where they would otherwise all collide, right? And they're all able to avoid each other and still find their way to the other side of the circle. So over here where you see these little jumps happening, that's where our CBF is kicking in and it's saying, hey, we need to modify our input to maintain safety. Okay, great. So let's discuss a vision-based CBF-QP, all right? So in that previous one, right, what we assume is that we actually know the positions, velocities, accelerations, whatnot, to all of the other turtlebots in the system, right? And that allows us to apply a set of, n CBFs if we have, say, like n other turtlebots in our system, okay? But what happens is with real world data, we have a little bit of a different constraint now, right? Now, let's say that our turtlebot only interacts with its environment using LiDAR data, okay? And this is just going to return a point cloud in the turtlebot frame that, tells the turtlebot a set of points that, might be of obstacles in the environment, okay? So what we want to do at this point of the project is we want to come up with a singular barrier function, so one barrier function h of q, that takes in a point cloud and it takes in the current state of our turtlebot. It's all we know in this case, and that applies those barrier function constraints to figure out the safety of the system, all right? So we're taking in this sort of sample of points of obstacles in the environment. We could have a whole bunch of turtlebots still, and we're using just those discrete points to figure out if our system is in a safe state or not, okay? So there's a lot of different methods for doing this. This is something that you guys will figure out on your own, what works best for you. You could apply a control barrier function over the closest point to your turtlebot in this point cloud, right? What you could also do is you could apply clustering to identify different turtlebots in that point cloud. And then say you could apply a single barrier function over the distance to the closest cluster that you find. There's many, many methods of dealing with this, okay? The main idea is, given this entire point cloud, we just want a single barrier function that'll give us safety, okay? So since our data is a little bit imperfect in this case, it's going to be okay if you get deadlocks. That's going to be allowed in this scenario. If two robots get stuck in a face-off, that's not a big deal. Okay. Finally, let's talk about what we're actually going to implement on hardware. And this is the breaking CBF-QP, all right? So due to some limitations of state estimation on the turtlebot, we're just going to be implementing a simplified version of the CBF-QP on hardware, all right? So we won't be incorporating that full, second order constraint where we had two derivatives of the barrier function and we nested everything inside feedback linearization, all that complicated stuff. All that we're going to require is that instead of having it steer around our different obstacles like before, we'll just have our turtlebot stop in front of obstacles, right? That's going to be sufficient for us. So now we're going to solve this much simpler optimization problem, all right? In this case, k of q is going to be our input u directly from our feedback linearizing controller, all right? So that's our tracking input all the way on the outside that allows our turtlebot itself to follow this desired state, okay? So that's what k of q is. And then u is what we're optimizing for, right? That's our actual safe input that we're trying to send to our system. So it's not like we're nesting it inside feedback linearization in this case. This is all the way in the outer layer. We're just solving directly for this input, all right? So because we're just using this outer layer directly, it turns out that we could just use a single derivative of our barrier function before an input term will show up, okay? So that's why we only have this simple barrier function constraint to tune here. So in this case, we're going to be taking the derivatives of h dot, right? Derivatives of h just along the trajectories of our full nonlinear system, okay? Q dot equals this stuff over here, all right? Because this is our actual nonlinear turtlebot dynamics. Okay. So let's discuss a couple of other things. Now, the barrier function in this case, h of q, should actually be exactly the same as your vision-based barrier function from your simulation. There shouldn't be anything that you'll have to change, okay? Now, it turns out that you might have to retune a couple of different parameters when you're actually, working with things in practice, but you'll find what works best for you as you go along, all right? So when you implement this controller on hardware, there's a couple tests that you could try to make sure that it's actually working, all right? So maybe you could stand in the way of the turtlebot. The LiDAR should pick up, if your feet are in the way of the turtlebot, right? And the turtlebot should brake if you're in its path and ensure that it doesn't collide with you. That's one test that you could run, all right? Now, another thing you could do is you can move towards the turtlebot, right? And if you move towards this turtlebot, it should actually back away from you using the CBF, all right? To ensure that, it doesn't have a collision and that the system is still safe. Okay. So when you actually implement this in practice, it'll kind of be like there's a little force field around this turtlebot. And let me show you guys what that looks like, all right? So we've here trapped a turtlebot in between Han's legs. There it goes. And when he pushes his hands towards it, he can actually get the turtlebot to move in different locations. So let's say he brings his hand closer to the turtlebot, he can actually push it away from him. Right? That turtlebot's ensuring that there's going to be no collisions with Han's hand. Okay, so this is what you're going to be implementing on hardware, this simplified version where we just have this braking constraint. All right. So just remember, these are a couple ground rules for using the turtlebots over here, okay? If you have any questions, do let us know. Otherwise, good luck on your project.